Recording in progress.
Okay. Okay, great. For people joining us, we are talking about trees and their support in upcoming version 13 of Orphan Language. All right. Tree traversal orders. This is going to be a big deal because this is very related to the whole multi-computation story. So I'm going to be interested to see what you have for tree traversal orders. So what should I be looking at here? Should I be looking at the
reference page
for traversal order?
Yes.
How much does this follow what was in my combinators blog post about these different namings and things like that?
So
how much does it follow that?
Yes, so each of these orders has different names, and we have included how you called it in the blog post as one of the possibilities. So you see the outer, inner, outer, etc. The middle of the page.
How did you make these pictures?
Team did them as created. I mean, they are great as usual.
What? I mean, there's a code that makes them.
I guess so. That's Tim. He's great.
Well, but I mean, are they drawn or is it code that makes them?
It's code.
Yeah.
But he has his own system to make these kinds of things.
Okay, can we put it as a WFR? Because I'd like to use that code. That looks very useful.
No.
Why not?
Because it's not a code in that sense. It's code underlying an editor that you need expert knowledge to use.
Well, we should have something like this where we can draw diagrams like this for more complicated.
Fine, that's easy to do, but this is a very general purpose system. It's not for this.
Okay.
So there are two types of diagrams in this page. So these first lines try to explain what the individual parts of ordering are. And then further down, there are examples of the 12 possibilities that you can combine them.
Okay, hold on. So eventually this will need to be an option to map as well.
Well, that's one part of the discussion. I don't know whether we want this to be tree traversal order or to affect everything else.
Well, I mean, we don't yet have the equipment to do this for map, do we?
I don't think so, but that's why this could be tree traversal order, or we leave it as traversal order and then.
Well, I know, but the question is design-wise, would it work for map?
Some orders, perhaps not all of them.
Have we thought it through?
We have thought about trees, not
no,
so
I understand that, but that's not what I'm asking. So the question is, are trees general enough? I mean, they don't deal with heads, for example. And expressions, we can have heads, which is a different kind of thing from what we get in trees, correct?
Here we have the data, which is kind of the equivalent. But in a sense, the nodes of a tree are all of the same type, while in trees we would have to worry, in expressions we would have to worry about collections of heads. It's a bit like allowed heads for arrays. What do we consider to be part of the array hierarchy?
Yes.
My point is that to understand the difference, perhaps this second diagram is clearer first.
Which second diagram? This one here?
No, the data set with all these 12 trees.
No, these are nice. I mean, this is useful, I think.
It's nice. I'm just talking about understanding.
I mean, it would be even more useful if there was some color coding that indicated what's top and what's bottom. I mean,
that's selected by the nest line.
Okay, so let me understand this.
So the first line is saying, these are the structures you should worry about. And then the other two are saying, do you visit them from top to down?
Well, they're not
up?
the only structures you should worry about. They're not at all the only structures you should worry about. Right? I mean, there are many possible orderings, and those are definitely not the only ones.
No, but what we are saying is that we have 12 orders, and it's a grid of 3 by 2 by 2.
Okay, but let me remind you, just as you might know, about what the actual story with these orderings is. Let me show you a picture, which I think I've shown before. Let's see, here we go. Okay, that's an ordering, right?
Yeah.
And in general, there are large numbers of possible orderings given by these young tableau and things like that, right?
Yes. Yes. So you're thinking of every single permutation of the nodes is a possible order.
Well, subject only to what's time-like separated. Right, the time-like ordering has to be respected, but everything else is up for grabs.
You mean that for the young tableau or in general? Because we have traversal orders that go the other direction.
Okay.
Right. So we have bottom up and top down. But for example, I'm looking at your third one, in which you first go left, then right, then left again. We don't have that particular one, in which is oscillating.
Yeah, I understand. I mean, in general, there are a large number of possible, orderings, and we can. This is the old problem. How do we? I mean, this is the problem which we're going to talk about extensively in this whole multi-computation business. What, there are ultimately two kinds of ordering that are relevant. There's traversal order of a static expression, and there is there's evaluation order. Okay. In other words, once you've evaluated something, then that defines a causal graph of evaluations, and how you traverse that is a different issue. Like for example, do you evaluate the third argument before the first argument, or do you evaluate the arguments in order? And then once you've evaluated an argument, do you keep reevaluating the result of that argument, or do you wait and come back up and evaluate the function that applies to all those arguments? Did you get what I'm saying?
Sure. Yes. But I mean, then the question is, what's useful?
Well, yes, Roger. I understand that question. That question is a question that I've asked for the evaluation sequence for 40 years. Right? And I think now what we have is a beginning of an understanding from physics, which we're hopefully merging with computational ideas to see what is useful. And the answer is that there are a variety of kinds of reference frames that are useful, or that seem to be the things, that get talked about in physics, and that are also the things that get used in logic programming, probabilistic programming, whatever else. I mean, look, the idea of having a traversal order for trees is a very fine idea. I'm just saying this is the beginning of a story, and we don't want to lock ourselves out of some interesting part of the story by being too naive about what we're doing here.
Sure.
Okay, so
I can tell that an important thing, as a matter of our own development, is that we have avoided the evaluator when we need speed and sometimes for non-standard traversal orders, but in particular, not redoing things too many times. So just do sort of a single pass through, for instance.
Yeah.
And I'm guessing that we're going to be able to do those with trees and not have to go to
What are you talking about? I mean, that's not relevant.
code.
That's not what I'm saying. That what I'm talking about evaluation is not, I mean, that's not relevant to this. This is the pure structural walking of an existing structure, not a structure that's changing out from under one.
No, I'm not. I'm just. We have to. If you use expressions, there is an evaluator in the way, and I'm just saying it slows things down because it keeps doing.
What
things.
is this? What is this? Is this new or is this like millions of years old?
It's old.
Have you even seen this?
What is it? Oh, this
It's
is
a
super
tech
old, probably.
note. Well, then why didn't it get updated or revised?
It should be.
Yeah, we should work on this.
Okay. Well, that's a lovely
I mean,
thing,
so
but
tree plot doesn't support tree yet.
what is tree plot?
It creates a graphics out of a tree graph.
Well, it should support tree. So it comes from here, right? Come on, guys. These pieces have to be connected together. I mean, just have tree plot say tree graph of the tree. You know, if it's a tree, to do a tree graph on it for now. That makes sense?
Yes, yes. And we are planning to update also tree form to have a closer graphical style to tree.
Okay. Okay. Let's look at this traversal order thing.
Yeah, so these are examples showing numbering the nodes as you visit them.
Yeah. God, I wish there was a way to do that without side effects.
What do you mean, side effect?
Well, an n equals 1, you know, n plus plus. I mean, is there a way to do... This would be like a tree fold. Does tree fold also have a traversal order?
Tree fold is specifically depth first.
And why is that?
Tree fold implements depth first evaluation. That's what it does.
I don't understand. When you have a tree and it's gradually adding on more elements to the fold.
Yes.
Why does it need to be depth first?
Because it's visiting, it's adding more elements as it goes down.
It's not adding elements. Like you start at the leaves and you are applying a function to your subtrees and percolating a value up to the top. You can't apply the function if you haven't computed the inputs to the function.
But would there not be a function then that would be a progressively folded function, just like you fold over a list? Why can't you fold over a tree with a certain traversal order?
So scroll down to the properties and relations on, or no, it's on the tree map page. You can functionally do the same thing as tree fold using tree map.
How?
It's in properties and relations.
Don't forget the redness there. Forget that. Don't forget that.
Mm-hmm.
Right? You understand there's not a confusion about that. Right? Is there a problem with that?
No. It's just adding.
Yeah. Okay. Fine.
To
okay.
syntax coloring.
Okay. So where am I supposed to look?
That's this example here. So this is mapping this function that's doing what you're saying, like progressively mutating the tree. And the end result is that tree fold ends up in the root. By the way, I think you need to update your documentation.
I just did moments ago.
Okay, I'll check on mine.
Do I need to do it again? Okay. The question from Ethan here. Are we going to have HTML, XML, JSON examples, by the way?
We have some examples on Nest Tree, but probably not in all of the places we could put them.
Do we have a reasonable plan for actually getting like XML into tree form?
Yeah, we plan on adding that to expression tree after 13.
Okay.
It's actually one of the main objectives for 13.1.
Okay. Okay. There's some suggestions on the live stream about examples about creating trees and so on. Okay. Right. Dan is commenting on a live stream about should they have a default. They do have a default. The default is depth first, isn't it? These functions do have a default.
Yes, the default is depth first.
Okay. All right. So let's right. Okay. Well, now where are we looking here? So we're looking at traversal order again. I mean, this is a complicated subject. Okay. In order. Why is that? I don't understand what this means.
That's a variant of depth first that's only defined for binary trees. And we don't have that in this version.
Why isn't it defined for any k-ary tree? Because it has a digital order.
In order means visit your left subtree, then the parent, and then the right subtree. If you have more than 2 children, then you have more freedom. It's like visit some of the children, visit the parent, visit the rest of the children.
I see. Why is it called in order? Does it not have another name?
Not that I know of. It's called in order because there's also post order and pre-order. That's what we're.
No, but what it is it's in the order it's drawn on the page, right?
No.
Yes. Left.
I mean, if you space
parent, right.
Oh, what do you mean? Why do you think that?
No. See, so you went to the wrong node.
What is the order again?
First left.
I need something with numbers so I can read it off.
Well, those aren't binary trees, but I can make you. How do I make you? What's the minimal way to make a binary tree with numbers?
Complete k-ary tree.
I say k-ary tree.
Complete k-ary tree.
Why is it complete k-ary tree?
Oh, I mean, that's fine. Yeah.
No. What's the difference? What is complete k-ary tree? I've never heard of complete
k-ary tree. Takes the size of the tree. Complete k-ary tree gives a full tree for however many levels.
Okay. And then how do I? And so if I say graph tree of this, what the heck is that about? What's that about?
This is a bug I've fixed in the prototype build.
This is the prototype build.
Yeah, it hasn't come in yet. So try running that in 12.3 to get the tree.
Why is it so slow? All right, what's the order now?
So it would go 8, 4, 9, 2, 10, 5, 11.
Okay. You know what? That's exactly what I said, or what I was trying to say, although I didn't say it properly. It's left to right order on the page. Right?
Okay. I don't think that communicates so well.
Right, but it is what it is, right?
Sort of in some way, yeah.
What do you mean, sort of? It is exactly that. An in order is in order as it is drawn on the page, right? That's what it means to be in order.
No, in order refers to the fact that the parent is in between the left and the right.
But the reason that that's
parent
natural,
after them, and pre
yeah, I understand.
Before. That's where the terminology in order came from.
By the way, has this been hooked up to the code structure stuff in the function repository?
No.
Are you aware of it?
Yes. We're talking to Chris.
Okay. Does code structure work on Wolfram language code? Does anybody know? So this will make a tree, right, from a piece of C code.
Mm-hmm.
And I assume it has a tree representation in addition to this kind of representation.
It represents it using code element. Which is
okay, I understand that, but I'm saying that just as text structure, which presumably you're going to have a tree version of this.
Yep.
So I mean, this has, what is it? It's constituent graphs, right? So what are you going to call the version of that gives a tree? Right, so that is a tree, isn't it? I mean, would that be, that is a tree of your kind of tree, right?
No, that's a graph.
No, I know this particular one is a graph, but I mean, there's nothing structurally about this that couldn't be your kind of tree, correct?
Right. So the plan is to have an expression tree to be able to eat these and interpret it automatically. So expression
Right.
tree has a second argument in which you can specify the type of thing you are ingesting. And so it will be automatically able to detect some of them.
Expression tree what? Has a...
But if this is a graph, shouldn't we just directly get a tree as a property?
Yeah, I mean, shouldn't we be able to say graph tree of this?
Well, sort of can, I guess, but
it does it work or does it not work? I mean, that says that is completely different. It's got noun phrase 1.
No, so that has vertex. You're looking for some way to convert a graph to a tree and use the vertex labels as the data, which we do not have.
Okay, although that seems useful.
Underlying vertex names.
Right. Okay, you're just using underlying vertex names. Right.
Mm-hmm.
Okay, but I mean, it does seem useful to have that, but this structure looks completely different, right? Why is the structure so different?
It looks like it's a different root.
What's the deal here? I mean, that seems like it's the root here.
Yeah, there's complicated issues with determining root vertex when you're converting between tree and graph. We're aware.
Why? I mean, if I took this graph and I just said, what's the vertex within degree 0? Why is that hard?
Well, that's not necessarily what is the root. The root is just whatever layered embedding happens to put at the top, which could potentially have nothing to do with the direction of the edges or anything like that.
I see. So this thing, in fact, this thing is not indicating the directions of the edges and probably should be. It doesn't know that this is a directed graph, is what you're saying.
Right.
But so that arguably is a bug in the graph representation of constituent graphs here, because it should know.
Yeah, so
there shouldn't be ambiguity.
What graph tree is doing right now, and it's just a heuristic, is it looks for the first vertex in the vertex list that has a maximum out component and uses that for the root. So if you happen to have a root and then all edges pointing away from it consistently.
So can I say what the root is here?
Yes. Second argument.
Okay, I wonder what the name of that vertex is. What the heck is the name of that vertex? Sentence 1, I would assume.
Lowercase.
No, I don't think so. Sentence 1 there.
Well, there's a lowercase sentence 1 in the vertex list as well.
This looks like the correct one. I don't know why there's lowercase sentence 1 as well. But I don't know what stuff 1 is. Oh, that's stuff.
It's
I
not
see,
the
that's
right
the-
one. You didn't. I think it is the lowercase sentence 1. Well, in any case, it's one
It's
of them.
not. Yeah, okay. So
But that's the other thing is the order of the siblings. You know,
Yeah.
we also don't necessarily get that.
know that. Yeah, you don't know that from a graph necessarily. Right, but clearly we should tag that. I mean, clearly, okay. So for text structure, we do know it because it's just text elements, but they were turned into a graph for this purpose with a special layout, and that's not adequate.
Mhm.
Um,
I mean, the graph layout is determining some order that it puts them on the screen. So in principle, we could match it.
right. Okay, back to traversal order. T-spec. Okay, where is leftmost, innermost?
So we did not, in the last meeting that we discussed this, we decided not to have leftmost, innermost, and innermost, leftmost, because it was confusing that it mattered what order you put things in. But all 8 of those traversals in your combinators blog are those are the 8 variants of depth first and breadth first.
Okay,
And then leaves first is something new.
okay. So in the combinator thing, so what this is in the end is a thing that is a generalization of lexicographic ordering for part numbers, right? That's what this ultimately boils down to, yes? Do you understand what I'm saying?
With the caveat that leaves first, you can't get that pairwise. You need to look at the whole vertex list. That's
But that's not what I'm
some
saying.
kind of a
What I'm saying is,
generalization.
no, that's not what I'm saying. I'm saying, oh, I see what you're saying. You're saying there is a
So
global
I have
order.
examples on this page comparing some of these traversals to like lexicographic sort and sort, if you're interested.
Okay, yeah, I am interested. But I mean, you're saying that normal sorts can be done by transpositions, but the leaves first sort cannot be.
Right.
Okay. So, but I mean, the main point is that there is an ordering. How do you get the ordering out of? Is there an easy way to get the ordering out? Do you understand what I'm saying? Now, if I just want the order, right?
Like
if
the
I've got
order
numbers 1
corresponding-
through 10, how do I get the ordering? Where is it? Here. Okay. What's that? Is that those are positions, right?
Yeah. So I sorted all of the positions in numerical order and then decreasing length.
But wait a second. Wait a second. I'm
So-
simply asking.
So I don't think that you have the most updated version of this page.
Okay. Well, I can rerun my. Okay, just check it, please, because I just ran it. Just ran it. Literally just ran it. I'll run it again. But okay, but I'm trying to understand. What I'm saying is given a certain sequence of part numbers, every traversal order defines an ordering of part numbers. Do you agree?
Yes.
Okay. I want to know, how do I get out the ordering of part numbers to which a given traversal order corresponds?
Probably the easiest way is to do tree position of tree, comma, blank, comma, traversal order.
Okay. But is there an argument?
Isn't there a way of to just traverse it and throw the number? You know, where am I?
Well, you could throw the
probably
data.
sew them. Yeah.
Sorry?
You can sew it.
Yeah, sew it. I mean, yeah, sew it, I meant.
Yeah, so map has access to the data in the subtree.
I get all of this. I still think that for purposes, this is a fairly confusing area. And I think there may be an argument to do something which I already did for the combinators thing, of actually having a function that returns the sort of a bunch of part numbers with respect to these criteria. Just like lexicographic sort, you know, there is a depth firstness, so to speak. Well, it isn't depth first, but something different. Do you see what I'm saying?
Yeah, so there are orders defined that correspond to each of the 8 depth first and breadth first orders.
Orders in what sense?
Like a function that you could pass into sort, and it
what is that function?
Well, one of them is lexicographic sort. The other one would be,
but it's not an easy. It's a sort of miscellaneous.
Yeah, it's a messy thing.
Right. That's why I wanted you to update, because Jose and I.
Let's take a look here. What was that function again? Tree map.
Traversal order.
Right, but what I'm suggesting is that that we have a function that is even we have, you know, possibly one of the sort functions has traversal order, because, you know, look, when we do sorting,
that would work for depth first and breadth first, but not leaves first.
I don't understand that statement. In any situation, there are a sequence of part numbers. There is a definite ordering of part numbers, which corresponds to the traversal order. Yes?
Yes.
Okay, so why can I not give that sequence of part numbers and say, do leaves first?
I see.
And then what I'll see is a bunch of long part numbers coming first, right?
Mm-hmm. Or you have the shortest numbers first.
I thought leaves first was going the leaves first. Is it not the leaves first?
Oh, sorry. Yeah. Longest positions back. Yeah.
Right. So my point is, it seems useful to have something which will take a sequence of part numbers. Okay, so what you've done here. Okay, so base order.
That's got to be doable, Ian. You know, leaves first, because
of course it's doable.
Yeah, I mean, there is an ordering, so there clearly is a function that gives it.
I'm not sure about that.
What do you mean? It's a definite order. You've got a sequence.
What I mean is you can't infer the negative level from a part spec.
So I think what Ian is trying to say is that we can do sort globally on a list of positions.
Yes,
we cannot find an ordering function that
I know.
pairs.
I keep on saying this. Yes.
Yeah, so
that's why this is a different function. It is not sort.
Right. Yeah, I agree with you. It probably cannot be done by pairwise comparisons.
Yeah, it cannot. I'm sure it cannot be done by pairwise comparison. There are only, I mean, it's an interesting question. What foliations can be created by pairwise comparisons? That will be a criterion, actually, which I hadn't thought of for these kinds of foliations. Do you see what I'm saying?
Yeah.
Yep.
I wonder what that criterion corresponds to. I mean, that you know, this is like the story of reference frames and relativity, and there should be something to which the insisting that the thing be able to be done by local pairwise comparisons corresponds.
Right. Yeah, that's leaves first. It feels very global in nature. It feels like, yeah,
it
is pretty global.
Right, but the whole point is that that sort, when you do sorting, there is considerable arbitrariness to what matters, the length of the list, you know what I'm saying.
Yeah.
There are a variety of things that can matter. So, our sort function just has sort of arbitrary choices for that, because most of the time, all that matters is that it's a canonical order. But if you wanted to sort, so I'm suggesting that we have a function that is some kind of, I don't know, traversal sort or something, or part, or I don't know what the right name for it is. Traversal sort maybe, which takes a traversal order and sorts a list of what it interprets as part numbers into that traversal order.
So it's something that only works on part numbers, kind of.
Well, no, you could do it to anything. But I mean, look, Roger, the problem is if it isn't lists of things that have an obvious canonical order, let's say it's lists of lists, then you've got a whole giant world of other things that can happen.
Right.
You see what I'm saying?
I mean, I understand why we want this function for illustration purposes. I'm just thinking of why else.
Well, I know I used it a lot in doing stuff with combinators. It was very useful to have that actual
to
function.
then sort of map at or something like that, or
among other things, among a bunch of things. I mean, studying how many, what depth things occurred at, and blah 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 blah.
Mhm.
Now, conceivably, there are other ways to do those things, but I certainly found that function useful. But now, the problem is, for example, doing this for things which are like part numbers, which are one-dimensional lists of positions. It's not obvious that that's general enough, but it's a vast can of worms if you say that the part numbers are no longer quotes part numbers. They're no longer just linear lists that say which side of a tree to go on, but they're more complicated accessors. You see what I'm saying?
Mhm.
So what would happen, for example, if we have a list of position specs, which are kind of disconnected? So it's we are missing the nodes to connect to some position spec which is present there. So they do not form a true tree, say.
What are you saying? You mean there are things in the ordering? There are nodes whose position is not defined by the ordering. Is that what you're saying?
Well, I'm saying that if we have a tree and we extract all the positions, then we can do sort of the positions with the various traversals. But if we take a subset of those positions, I wonder whether the operation is defined.
If we take a subset of which positions?
Of the position of a true tree. So
right, for example, would 1, 2 come before 3, 4 in leaves first? I don't think you can tell.
yeah, if those are the only two positions you have,
Yeah.
it's like
I see.
having
So
disconnected.
absent a tree, you're saying without the actual tree in place.
Right. Because perhaps what we need here is a tree map indexed with a traversal order. And then you visit the tree.
And you can get and one of the things you can do
Which
is
is on our list. That is on our to-do list.
spit out the index.
Yeah, why not just have something which is a tree index list, which has a traversal order?
Right.
What would that be? That's essentially
that's
tree
basically
node.
just tree position with a blank pattern.
I guess so. I mean, I guess is that a tree? No. So you're saying if I take something like this, oops, that's not the right one. And I say tree position. Okay, great. So that with a traversal order.
And then specify traversal order goes to breadth first.
Some autocomplete's missing there. Do you understand?
Yeah.
What's that?
Yes, we will add it.
What's that?
Bug, put all before traversal order.
All here.
I'm sorry, 0 to infinity.
Whatever. Okay. Anyway, but I understand the idea.
That will work.
Okay. 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 Well, fair enough. I mean, how confident are you about this design?
Well, it contains the standard orders, and it contains the orders you found for the combinators and more.
Okay.
And it's kind of a complete table. So I think that's what is shown in the table of 12 possibilities. And we can always generalize it. We find more. I mean, more orders. We just introduce more names.
Okay. That's nice. I mean, it's great we have this. I mean, we really should think, should this be tree traversal order or should it be traversal order?
Right.
Do we think that in the end, we will be able to use the exact same traversal order for expressions?
My only thing is we have multiple concepts of how to transform an expression into a tree. So if you use the same traversal order, but two different expression trees, it's going to be doing something.
All right, let's call it tree traversal order for now. It may subsequently just become traversal order.
Okay.
That makes sense. I mean, and it will be really good to do a study of how this could be applied to expressions, because it may be very obvious that the same exact thing can be done.
I think the safe choice is tree traversal order.
Okay. Tree scan, fine. Position support. Okay, tree map at applies a list of positions, great. Position patterns, okay, great. These were things that I was reporting, right? I mean, I tried this and it didn't work, correct?
Yes, yes. And in particular, some of them only supported one level, like a single integer index. Now they support full deep positions.
Okay, so this redesigned extended level specs, what is that?
Right. So an issue with trees that we don't have with expressions is that when you map at a given level, you have to specify whether you mean the data of the tree or the tree itself.
Mm-hmm.
And so that's why the level spec has an arrow with an element. And then there you say, I'm referring to the data or I'm referring to the tree. And there is
But where does, I'm sorry, oh, here. Here.
Yes. Then there is this original tree, because when you are mapping, you are changing things. So do you refer to the already changed tree or the original tree before it was changed?
What does map do? Map just wraps
map is like tree, except it inserts as a tree, and this is something that affects the data at a particular subtree.
Right. So the typical operation you want with trees is that you have data at each node and you want to map a function to a subset of nodes, say. But if you are mapping on trees, then there is a question of whether you want the tree before its internal nodes were changed or not.
I'm sorry. Say again, what does map do? I mean, map just wraps an F around everything, right? So if I have this expression,
right?
So
in tree map, it would be like as if you inserted a node above every existing node.
Oh, for goodness sake.
How
do we get that? What's that?
Or
how do I get that as an expression?
First, convert it to first do graph tree,
right.
and then tree expression.
Whatever.
12.3. That'll work.
Okay, there we go. Okay, so now if I say map F onto that at all levels, that is effectively the outer Fs are applied to the, by when they, at the time when the outer F sees something, its inner F will have been changed,
Mhm.
right?
Yes.
Right.
And that's part of the evaluation process. So now what are you saying here?
We're saying that that if you do level spec arrow tree, you get this kind of behavior. Where the Fs see the other Fs.
Okay, an original tree?
It would be each F gets the sub-expression of the original expression without any Fs.
Is that something we could imagine supporting in map? No, because we don't know how to put the thing back together again.
Right. I think this is a new freedom that appears with tree.
And why is that again?
I think it's with expressions would be something like mapping on a deep expression, and then the result we put it as head only, rather than replacing the whole expression you just mapped.
Yeah, I get it. I think there is an analogy there, though.
Perhaps we can always do the mapping through the tree and convert at the end again to an expression.
I know. One question is whether original tree is the right name, and whether it's data or subtree should be the the first two, right? What are we calling the when you extract? Don't we call it subtree as an accessor when you're extracting the subtree? Do you understand what I'm saying?
Isn't it tree part or something?
There's tree extract.
Okay, but what are we calling? I would have thought that this first case here was more naturally called subtree than data. I mean, than tree.
We could.
Well, the description uses subtree to describe it.
Yeah, always the sign. Okay, now the last one where you call it original tree. Is it the original subtree? Yes, it is. That's what it is, right?
Right.
Why do you say the previous applications of F? Because it depends on the traversal order, whether they're previous or not, doesn't it?
Right.
So you probably shouldn't say previous. Sub-applications, right? Applications to the subtree.
I see.
So I recommend just subtree and original subtree then. Does that make sense?
Yep.
Okay. All right, onward here. What's level spec all now?
0 to infinity.
Okay. Tree data. Now take a level spec rather than a position spec. What's that about?
Yes.
What does that mean?
This is in hindsight an error. We designed in the previous version this function taking position spec in the second argument, and then we realized it's much more useful to have a level spec. So this is a design change using the fact that it's experimental.
Data of subtrees on levels specified by level spec. So this is like a level. This is like the level function. Is that correct?
Yeah, so now tree data and tree level, I would say both of those.
Sorry, I don't understand. What's tree level?
It extracts subtrees, tree extract, and tree data extracts the data.
Right. So these are all variants of tree extract. Tree extract is the powerful function that can extract anything. And then to help in readability, we have tree data and tree children specialized in extracting.
Okay, but tree data of a single tree gives the single data. Tree data with a level spec is giving a list, correct?
Yes.
Yeah.
That's icky. That's really icky. What was it doing before?
Instead of having a level spec in the second argument, it was a position spec.
What kind of position spec? Multiple positions or a single position?
A single or list or anything that's supported by tree extract.
Okay, but a single one there would return the raw data, not a list of data, correct?
Yes.
Okay, so this is a mess, right? Because this is saying, I mean, I'm not really that keen on this. I think it's a mistake because I think this is a mistake.
I mean, the mistake having the generalization. I mean, it could be
Yes.
just a function that extracts the tree data.
That's what I'm thinking, because I think that if it is useful to extract tree data on a given level, the problem is that to have something where with a single argument, it's got a single object. With two arguments, it's got a list of objects. That's really not wonderful.
Mm-hmm.
And the functionality where you can extract the data, I mean, what's the relation between tree extract or tree part, tree extract, right? And this function. So this is going, can you in tree extract use an arrow data part?
You can directly use tree data in the position spec.
Tree data itself or arrow data?
No, literally use tree data in the part spec or use 0, their equivalent.
Yeah, the position spec for trees is very ambitious, following what XPath and other systems do. So you can use more things than in extract.
So this is an operator form of tree level, is that correct?
Mm-hmm.
Right.
So, but why aren't you supporting the same kind of thing that you showed in tree map, where you have arrow data,
Well, so currently we only have extended level specs, but for example, for tree map we are currently just thinking about having extended position specs, but that's not a bridge that we've crossed yet.
The extended position specs means just like you can say (0) and get into the head of something, you can say arrow data here and get into the data of something. Is that correct?
In a sense, but because here we have lists, we can also string things in the list. So you can have 3, 2, 3 data, and then you enter the tree data, and you could even continue within the tree data.
Sorry, say that again.
Yes, so in the standard position specs, you can have a list of numbers, and you progressively go deeper.
Yep.
So here you can also, in the list of numbers, you can insert tree data, and then you jump from the tree to the data of one element, and then continue within that.
I see, within the data. So just like 0, you can continue within a head too.
Exactly.
Yeah, 0 and tree data are exactly equivalent in tree extract.
So again, why is there a need for the arrow data thing in tree map?
Because level specs don't have that freedom.
Exactly. We're talking about level specs, not position specs. So what we need to extend is level specs.
Yeah. So why isn't it the same thing for a level spec? That I see a level spec is just a number, and this is saying the last number, beyond the last number. So in principle, we are missing something in level specs, because there could be a level that jumps to the head and then keeps on leveling, so to speak. Do you understand what I'm saying?
Yes.
So if you say level 2, you say level 2, now on level 2, go into the head, and then go down another 3 levels.
Right.
And we don't have a way to represent that right now.
Yes. So as I was saying, the languages for positions and levels in trees are more powerful than the ones we have for expressions.
Right. The problem here is that yeah, Ethan is commenting, level specs with named axes connects back to tensor operations. That's correct.
Mhm.
And we should discuss this in the context of our array summit that's coming up.
Okay.
Kind of important, actually. Okay. All right. Let's see. Wave is commenting. It would be nice. Okay, what happens with highlight tree? It would be nice to show evaluation as the successive lighting up of a tree. Yes. We've done experiments with that for at least 35 years. It wasn't very useful back when we started off doing it with things like trace. All right. Okay. So let's take a look here. Okay. Have I gone over most of the things here that are relevant? I mean, I consider this a little bit on the messy side, but I understand why we're doing it, and I think that's the best we can do for right now. See, the problem is, guys, this whole multi-computation thing and the whole story of evaluation orders, which is what that is going to relate to, is related to this, except evaluation orders. So this is the conundrum. There's both static construction orders, if you see what I mean, static expression traversal orders and evaluation orders. Both have orderings in them. Am I making sense?
Yep.
And I think the parameterizations of those orderings are really complicated. And I think that's for that we are going to require, and you've started building kind of a language for specifying those traversal orders. But it's going to have to be generalized for evaluation orders and for more complex traversal orders, probably for expressions. I'm just concerned that we're not, look, I think with tree traversal order, we've got this definite thing where we're boxing ourselves in enough that it'll be okay. All right, tree visualization. Tree layout. Okay. So tree layout is the analog of graph layout, correct?
Yes.
Specify the style for subtree elements by position. What does that mean?
It's a bit like what it's done in grid or dataset, that you specify collections of subnodes, and you can specify the styles for them. And so here we have two sets of options now, what we call the global options that affect the whole tree, and the local options that affect individual nodes.
I see. That's what tree element is.
Exactly. The tree element is the language to specify locality in that sense.
And how does that work now? Oh, I see. It's position to style. Wow. How does that relate to what we do in grid, for example? I think we have a similar syntax in grid.
Exactly. It's the same thing.
Okay. And that pattern could contain data. Well, that pattern, could that contain tree data inside that pattern?
No, so these either need to be explicit positions or patterns that match explicit positions.
Oh, why can't this be at the tree that is gotten by going 2, 3, data 5, 6? Do this. See what I'm saying?
Yes, I guess eventually could be. I mean, at the moment,
I'm we don't need to check the design is going to work for that. That's all.
Okay.
Seems like there's not a problem with that.
Mhm.
When do we get hyperbolic tree layouts?
Do you mean these circular ones with accumulation near the
Yes.
boundaries?
You can probably get them for 13.1, but there were things to be sorted.
Okay. Okay. So now tree outline, what's that? What is tree outline?
So yeah, so this is a function that existed already, and it's a collection of openers. It allows you to.
I never saw this.
No?
I have never seen this. I never saw this.
Okay.
Grumble, grumble. I never saw this. This was never reviewed. Sigh.
Yeah, we may have forgotten it in the previous cycle.
Sigh. Okay, so here you now claim you've got a truly random tree.
Mm-hmm.
We need to look at this function in more detail. This is really kind of impoverished, in my opinion. I don't know why it doesn't work if I click that. We never reviewed this. No way I would have agreed with this. I just don't think this is quite right. I think the basic functionality is interesting. I just don't think it's quite right. And I think also that being able to cell print it across into multiple, cells here will be very useful. See what I'm saying?
I see, rather than a single cell, the whole thing.
Right. I don't know what it should be, but I think that yeah, I mean, that's reasonable to have open subtrees, but I'm telling you, this is not very good graphic design, and I don't think it's good UX either.
Mm-hmm.
Can we come back and look at this some more, please, and make sure we have designers in the meeting?
Yep.
Okay. I mean, I would suggest that this thing be a more obviously tree-y thing, or at least have an option to do that. Maybe this case is a bad case of a random tree with just numerical nodes. What happens if I say, how do I get a tree out of a dendrogram?
I think
you understand what I'm
it's just
saying?
a graph, right?
Well, let's find out. Okay, so here, if I say dendrogram, does that make just a picture or does that make a tree? Okay, so how do I get the tree out of this? There is a tree here. How do I get it?
I'm not sure we are prepared for that yet.
Okay, something we need.
Yep.
So that's just a graphics.
I would assume maybe it's dendrogram tree. Maybe we need a dendrogram tree function. I thought we actually had something like that. We have, clustering tree.
Does
clustering tree return a tree?
It returns a graph.
That's probably wrong. That's probably wrong. In modern times, that's probably just wrong. We should look at changing that. It's not the best thing in the world, but it's better than having, the thing, or maybe we call it dendrogram tree and make that be the one that produces a tree and deprecate this one. Do you understand what I'm saying?
Yes.
But there's got to be a way to get, this is a tree. Get me the tree. How do I get the tree?
Right. So what we have done in other cases is to have an additional argument in which we specify, for example, whether you want a sparse array or a structured array or a normal array.
I know. But it may be that we should look at these cases and see whether in fact it's useful to have a graph or whether you always want a tree.
Well, because we will be able to change from one to the other.
Well, not if we
with tree graph or graph tree. Doesn't matter.
Only if there's tagging information. Are you proposing to put the tagging? Look, I don't like the function which ends with the word tree not being a tree, since we just set up a whole, graph tree family where it always is. If it ends with tree, it's a tree.
Right. I mean, I guess this function preceded the work on tree.
Of course it did.
Yeah,
by a long time.
Yeah.
I mean, we even discussed the fact, I remember, talking about this in the context of trees, and maybe we can, we got to figure out how to make this thing a tree.
Mhm.
But we're probably going to have a differently named function that makes the tree. Does that make sense?
Yes. Yeah.
Marco is commenting something like a dendrogram-like visualization for tree outline would be cool. And that's a good question. Is given a tree, if I just want to display a tree in this kind of format, is there a way to do that? Right, like I've got this tree and I now want to draw it in dendrogram form. Can I do that?
Not at the moment. I mean, the plan is to have multiple visualizations for trees eventually, but we are starting that process now.
Okay, fine. But so, for example, making it a dendrogram, it's a plausible thing.
Mm-hmm. Yeah, there are multiple visualizations for trees. Yeah. So
I understand.
One of them.
But those will be done with tree layout or what?
I don't know. Most probably, they will require different functions because each one will have its own options to control.
I see. So it's the analog of yeah, okay, fair enough. Well, we should inventory those. Label collisions get extra ugly in trees, says Ethan.
Mm-hmm. Yeah.
What is the general status of label collisions? For example, in geographics and so on.
The problem is different in each situation. In geographics, we always can say, oh, this city name doesn't fit, so we don't show it. But with trees, we do want to show as much as we can. So the situation is different. So here it's more like a lighting. We could decide that from this node downwards, there's too much information, so we light from that point. Something like that. So this requires different algorithms.
Trees are complicated, in case we didn't notice that already. Surprising how much structure there is to them that is different from, I mean, it's interesting. We didn't tackle this before. And we kind of always assumed that they were sort of trivial, but they're not.
Well, someone even claimed that they're universal. Like you can even call them expressions and represent everything.
Indeed. At some level, the whole evaluation scheme, symbolic structure, and so on, that is the core of the language. It's a great example of knowing enough to make it work and not knowing so much that you freak out. Because at this point, I know a lot more about evaluation orders and all kinds of pathologies that can happen and non-terminating things and so on. And it will be easy to just say this will never work. It will just always, it'll freak out. But it turns out it doesn't, for reasons that are, subtle reasons of what people choose to do, rather than reasons of what's in principle there.
Wasn't it the case when you went for infinite order evaluation? I mean, until fixed point. Wasn't it Lisp before it had one-step evaluation?
Yeah, Lisp has one-step evaluation. Everybody told me that it was theoretically impossible to have infinite evaluation.
Right.
But they were deeply, deeply confused. I mean, they thought one of their biggest confusion was in the binding in a lambda, that if you say lambda x plus 1, they thought the way you evaluate that is by temporary binding of x to x plus 1. And they said, if you have infinite evaluation, that temporary binding will blow up.
And it will.
Well, it will if you do it with temporary binding.
No, but us too, if you set...
I know, but not inside a lambda. Not
right.
With pattern
Right. Yes.
The whole point about pattern matching is you don't have temporary binding. It is a pure symbolic transformation.
Right.
And the problem was that they were obsessed with the idea of variables and binding. And so they were very confused. And like I remember Dana Scott, and when I showed him SMP, and he said, I have this denotational semantics that's a sort of general theory of all programming languages. I said, how does it cover this? He's like, well, it doesn't. I'm like, okay, what does it mean to have a general theory then? it has call by value, call by reference, call by name, those kinds of things. But
Right.
this isn't. This is call by symbolic transformation, which isn't really a call at all. And that's how one evades the infinite evaluation binding issue.
That's
In fact,
interesting and pretty damn subtle.
yes, it's one of these cases where, look, the basic point is, it was obvious that you could make the transformation work. If you started thinking about it in terms of things like denotational semantics, your head might explode and you might think that it couldn't possibly work. Right. And yeah, but I mean, this is what we're now trying to roll back as we talk about multi-computation and we talk about the idea of, multiple threads of evaluation and so on and how they interact. That's what we have to now resolve. And that's why I'm so interested in these different traversal orders, evaluation orders, etc.
Right.
Because that's finally nailing that issue. Plus, I've said a million times, I had these two attributes of functions in SMP that determined evaluation order, which was simply incomprehensible to people, including me. But, this is the problem. And this is, by the way, I mean, at a bigger picture level, the problem of evaluation orders is the same as the problem of reference frames. And I don't know, maybe Jose wants to make a general comment about.
But I'm thinking the apart from that, I think that these traversal orders, it's about sort of information accumulation. Often when you do them, you have to do more than one pass anyway.
But information accumulation is the same story as observers.
I guess, yes.
Right. Observer is aggregating pieces of space-time or whatever.
Right.
So Jose, can you make a comment on, when you make a reference frame, when you make a, in general relativity, what are reasonable frames? What are reasonable gauge choices? How do you characterize that? By some continuity thing or what?
Well, I think that in general relativity, we distinguish the metric, which is the geometric thing that contains all the causality information, etc., from then the coordinate systems or reference frames, right? And those can be arbitrary, but there are some which are associated to some preferred observers. Like, for example, there is an observer moving through space and it's sending light rays and receiving them back. And it's constructing a frame of the vicinity of the world line of that observer.
Yes.
And there are some famous constructions like Fermi coordinates, which have a specific way of being constructed, and those are associated to an observer. But the important thing in general relativity is that for a given metric, you can construct any coordinate system you want. It doesn't matter which one it is. It may not be physical at all, but it works in the equations.
I understand that, but what I'm saying is, like, for example, in the case of, constructing things for, I don't know, naked singularities, the avoidance of naked singularities, those kinds of things, don't you end up with these bizarre foliations of space-time, basically, that seem unimplementable by a practical observer?
Yes, but those foliations may not be associated to any observer at all, but they are valid foliations.
I know, but the foliations are the evaluation order. I mean, look, there's clearly relationship between what we call an observer, what we call a foliation, etc. But the thing that I'm trying to understand is, we've got a traversal order thing. We've got these named traversal orders. Great. Just like we've got these named things like Schwarzschild, the Schwarzschild solution, the inertial frames, these kinds of things in general relativity. My question is, if we're going to say what is a reasonable thing to construct and what is not realistically constructible, that's what I'm trying to understand. Well, how do we parameterize? What I'm trying to understand is, how do we linguistically parameterize all reasonable foliations? Because, I mean, right now, we're just doing that by names in traversal order. Is there a more, if you could say, I don't believe in symbolic expressions. I'm just going to name, like Fortran or something. I'm just going to name all these different structures 1 through 14 or something, right? But I don't believe in symbolic expressions. My question is, when you're talking about foliations, what is the symbolic extensible representation of foliations?
Well, I think what we need to separate here is foliation from observer. Observer is a word line of somebody going through the space, and that observer can define only in a small region around him a truly physical reference frame, not very far. For if there is much curvature, if there is much gravity, it cannot be very large because coordinates will self-cross and there will be odd things. So there is a limit to the size of the physical reference frame. But then mathematically, we can construct any foliation we want as long as it's made of surfaces whose orthogonal vector is time-like. And that's the only restriction. They will probably have no physical meaning at all, but they are mathematically correct.
I know, but there are even ones of those foliations that get so wild that you couldn't realistically expect an observer. I mean, my point is, if we are simply parameterizing foliations, right? And we're doing so independent of the space to which they are applied, like inertial frames, we can do that in, well, this is what I'm trying to understand, is like part numbers are an example of something which can be applied independent of the expression to which they are being applied.
Okay, but is it the case, like, let's say that you do 2 or k passes of traversals, different kinds of these named traversals. Is there one traversal that could do it all? So you only had one traversal. Could it be more efficient? Is there another traversal that could do it and would be more
I understand
efficient?
the calculus of traversals.
Yeah.
What is the algebra of traversals, of how different traversals can be combined?
Yeah.
I wonder if anybody's looked at that.
But I mean, there's some, there's a point of being able to understand it. If you're going to use it, if we're building a language, you kind of need to be able to understand it.
Well, I know that's the challenge right now. Right. The question is, how do we turn this into something that one can understand? And, note that, see, this is one of the beautiful things. We've all been working with this symbolic transformation thing for decades, right?
Yeah.
But the things I was just explaining to you about temporary binding and, why things don't blow up and so on, we never had to think about that.
Right.
Right. And so the question is, for thinking about, right now, it looks really complicated, or specifying all these foliations, blah, blah, blah. It's like, oh my gosh, how are we going to deal with this? But I'm telling you, I think there's a way to simplify it by thinking about it the right way that is as clear, in a sense, as symbolic transformation rules are, so that you're not thinking about, temporary binding explosions and so on.
Right.
That is the challenge. I don't know how to do it.
I know of a very practical utility of what we do now, which is, as I said, this infinite evaluation, as practical as it is in many contexts, it's a performance drag when you want to traverse a tree to collect information.
Yeah,
I'm saying. So this is going to be very good.
I understand that, but I mean, it's the same performance drag as saying, look, infinite evaluation is, in space-time, it's like going to the end of the universe before you wait.
Yes.
Before you.
That's a good way of saying it. Yes.
Right.
Pretty much.
So I mean, it's clear that's not a good strategy. In the case of for example, one thing we do not have in the case of an infinite evaluation, like a combinatorial evaluation, or even x goes to x plus 1, right? We do not have a way of capturing the temporary results, right? Take x equals x plus 1. Mm-hmm. There's no good reason, or another non-terminating recursion, like a combinatorial evaluation.
Right.
There's no good reason, like in combinatorial evaluation, I wrote this whole thing about looking at what happens if you just go X number of steps according to some evaluation order, right? And there's a whole rich structure. What's that?
Right. We're starting to look at other infinite computations, and it's pretty useful to truncate them. So for instance, if you want, there's a Grosvenor basis for non-commutative algebra, and it doesn't terminate. It's not finite, basically.
Mm-hmm.
But using the truncated, some distance out is often extremely useful.
Well, isn't that like real numbers? Finite precision real numbers are useful.
Right.
And I mean, insofar as there is a notion of computable numbers, you can just go computing them forever, but their truncation is useful.
Right. Is there a truncated infinite evaluation that's useful?
Exactly. So for example, with combinators, I was wondering if there's a way of representing, both the infinite trees as transfinite, numbers, and then the truncation somehow, some orderly way to do truncations. And that's the whole point of these foliations, is that they represent truncation slices.
Right.
That's the issue. The issue is, okay, so here's the way to think about it. If you have just a linear sequence, truncation is just stop at the nth point. If you have a thing that is a complicated recursive evaluation, like a tree, stop at the nth point doesn't really make sense. You have to say, what is the profile of where you stop?
Right.
And that's what we're defining with evaluation orders, traversal orders, whatever you call it. Or you could do that. You could take an infinite, given a traversal order, you could say, go n steps with this traversal order in this infinite process. Well, at least if we translate traversal order to evaluation order, which I claim is doable, but not trivial.
Right.
Isn't this interesting stuff?
I guess truncation is good when you know there is convergence, because if you truncate something that is going to go very far.
No, asymptotic series is not convergent, perfectly valid, really good.
I see. That's a good example.
Right. I mean, I think it is useful. I mean, look, the thing with combinators, I mean, honestly, I thought my study of combinators was pure kind of, well, not frivolity, but it's turning out it's very intuitionally useful for this stuff. Okay. Anyway, we should wrap up here, but let's see. Did the random tree, what do you mean by truly random? Didn't Don Knuth send us some code for some more random tree that turned into a WFR, I think? Are you guys aware of that?
Yes. And we have used those similar ideas to.
Okay. What does it mean, a truly random tree?
Exactly.
Yes, it means that in the previous iteration in 12.3, we were producing random trees, but they were not homogeneously, uniformly constructed, and now they are.
But what's the big space in which they're uniform?
Yes, so different structures, and if you permute the elements, the data of the tree, they give different trees.
Well, but what Roger is asking is, we can imagine a Markov process that makes a tree. This is probably not made by a Markov process. This is some other form of randomness for trees. What is the measure? In other words,
yeah,
go ahead.
Can you explain that?
Well, so for size n, there's going to be however many trees of size n, labeled trees of size n, and we just pick one at random.
I see. With uniform measure for finite trees of size n.
Mm-hmm.
Right.
That makes
I
sense.
see. So this is again the truncation process of. So this is like something like random samples.
We should describe that on that random tree page, in which that it's in this sense.
Yes.
Mm-hmm.
Because I think it might also be useful to say pick a random tree according to a Markov process.
Yeah. No, but we spent a ton of time, for these random graph distributions to make sure that they have the proper distribution, so to speak. And people actually found it for these degree graph distributions. People were just pointing out they weren't quite right. We had to go back and
Yeah, well, you can figure out whether it's right by just making a histogram.
Right.
Okay. Yeah, by the way, your comment about world lines and observers, Jose, is more complicated, right? Because in the quantum case, the observer is not anyway, there's just a messy thing. The observer is not localized in branch Hill space as the observer might be localized in physical space. That's just a totally obscure comment.
I understand the quantum case is even more difficult. Yeah.
And that's, I mean, that is one of the big questions is in physical space, we are a certain size, a meter, whatever we are. There is a question, how localized or not are we in branch Hill space? And that determines this question about the locality of the frame. It is quite lovely how all these issues are converging. Kind of makes one realize this is not actually as simple a process as one might have thought. I mean, in other words, one kind of has to understand quantum mechanics to understand how to do this. I mean, this thing that I've been wondering about for like 40 years of how to parameterize evaluation order. We need an idea. Roger, Jose, Ian, everybody, we need an idea, right? Of what is the idea for representing foliations? What is the idea for the disembodied foliation? I mean, in a sense, part numbers are a way of having a disembodied single position with the weird thing that just like coordinates have ranges, part numbers have ranges. You can kind of run out of expression space. You see what I'm saying? But part numbers are universal to all sorts of expressions. Levels are another example of something which is kind of a universal idea in at least tree-like expressions. And levels are like the cosmological rest frame in some sense. If Jose at least understands that comment, I think.
Yes, I understand there is some sort of preferred foliation.
Right, but that's levels represent the kind of from the root of the tree. Yes, that's right. I mean, from the root of the tree, they are n time-like edges to every point. Mm-hmm. Well, no, I'm sorry, they're not. They are the thing which corresponds to, oh gosh, what we're calling generational states. Anyway, well, this is a different discussion, but we need an idea. We need an idea about how to represent. How to represent. It's sort of a generalization of levels, actually. It's not a terrible way to think about it.
Well, it's the idea that Ian was showing in which structures do you first consider, and then in which order do you visit them?
You mean in traversal order?
Yes, this first diagram that there was in the page of traversal order, in which you first select the structures you will be visiting, and then you give parameters saying in which order you will visit them and inside them.
I mean, this is basically time-like, space-like, isn't it?
Yes, in this particular case. But perhaps there are others.
You mean other classes of evaluation orders?
Or other classes of structures, yes. So something that we have discussed is that the first diagram seems to suggest nesting. While we are not trying to communicate nesting, we are just trying to break the tree into disjoint sets, which is clearer on the other two, but not very much in the first one.
I think that's not surprising. Yes, I think that's the story of time-like ordering. It's because things follow from things, and so they get more deeply nested.
Right. So that's the important line. The other two are just saying, what do you do vertically and horizontally?
Yeah, I think that's less interesting. This is the true, foliation story.
Right.
This stuff here.
Mm-hmm.
Wave is asking, does the parameterization of evaluation orders include or separate between random access orders and connected orders? That's an interesting question, actually. Right, that's an interesting question. Does the foliation have connected, allow connected visiting? I mean, normally they don't. The most common ones in relativity do not. You know, you go, you know, you have an inertial frame, it's just slicing it, and you don't, it's more like this, it's the breadth first case here. If I'm not mistaken, those are the space-like slices.
Right. Those are true levels.
Right, which are tree levels.
Mm-hmm.
Space-like slices are tree levels. And a boost, what is a boost in a tree?
So when you say space-like, you mean they're space-like separated?
Yes.
Okay.
What is a boost? It should be the case that on a binary tree, you should be able to do a boost in which on one side of the tree, you are visiting things earlier than on the other side of the tree.
Yes, but I don't understand.
Isn't there some crazy operation, tree rotation? Isn't that used in isn't that
Tree
an
rotation
operation?
is useful for like self-balancing trees. They're useful for all kinds of searching applications.
What is it again? It's you rearrange a few of the nodes.
Yeah, tree rotation.
You're finding a new route, basically.
Yeah.
I bet that that's the same as a boost.
But we don't. This isn't something we have.
I bet that's the same as a boost. Ah, well, okay. I got to go to my next thing. But this is lovely. I mean, don't you guys appreciate how elegant this is all going to be when it comes together?
Yeah. Stephen, do you want to revisit this, or do you think we are basically done?
I think we're basically done. I think that we should make sure that that at least the three of us are in the conversation about this multi-computational language design, because I think this is going to be related. And I'm a little bit concerned that there may be things that emerge from that where we say, oh, now we understand this. I wish we did that in trees.
Right.
Okay.
Okay.
Ethan is saying, can we add red-black trees?
That's a data structure.
Yeah, it's a different thing. We have that, don't we?
I don't know. Wouldn't surprise me if we do.
Right. Okay. And there's also a request for plot theme for trees. Do we have that? Is that coming?
We should. I mean, we don't, but I think that's a good idea.
Fine. All right. Let's wrap it up. Thanks a lot. Thanks, everybody. Thanks to folks on the live stream. Talk to you all soon.